All right, so last time we had started this exploration with patterns. We'd noticed several kinds of patterns, but in particular we were working with number patterns. We had talked about arithmetic, which was what? What is arithmetic pattern? What does that look like? Yeah, every term you get to the next term by adding something. And then we had another one which is geometric, multiplication to get from one term to the next. And we talked about, we'll see how much you remember when you actually do your homework or start doing your group work. We talked about how we find these sort of general terms, like 3n minus 2 here, and 3 times 2 to the n minus 1. So we talked about those kinds of things. We also talked about the fact that, like on this one, part B, it wasn't geometric or arithmetic, but if we went sort of like a second layer deep, it actually became something that was arithmetic one layer beyond, like one more step beyond. We call those second differences, and so you have an opportunity to practice something like that too. All right, so example 3, what we're going to do is we're going to find a counterexample for the following. Now we did this in one of, now I can't remember if it was this class or my other class, but we do these from time to time. Your textbook likes to do these, where a student reduces something, or a student changes something, or a student makes some kind of a claim, and then you are going to put on your sort of teacher's hat and make this sort of a decision. Is it right or is it wrong? And kind of what kind of response would you give to the student? So in particular, this one just wants you to find a counterexample. So do you remember what counterexample meant from last time?
Something to prove it wrong.
Yeah, something that will prove it wrong, exactly. So a counterexample is an example, so it's going to have numbers, you're going to choose numbers, that are going to show that this statement, n plus 5 over 5 equals n plus 1, is wrong. So in general, most times anyway, counterexamples are something where you play around with numbers to see if they work. A little bit careful that you pick a number that will work, but sometimes lots of numbers work, and sometimes lots of numbers don't work. So it just depends on the problem you're working with. So somebody give me an example for n that you'd like to try. 6. Somebody else is about to say 1. All right, so 6 plus 5 over 5. And then the question, basically, you're asking yourself is this going to equal to 6 plus 1? So what is 6 plus 5? Would be 11, right? Over 5. So this is 11 over 5. What is 6 plus 1? 7. And is 11 over 5 equal to 7? No, this is not equal. So this is your counterexample, n equal to 6. And this is actually showing that it fails to make, that it really is a counterexample. N equals 1 would work as well. Most numbers will work on this. What is the one number that will not work? 0 will not work here. If you put the number 0 in, it actually makes it a true statement. So you do have to be a little bit careful. Usually the ones you have to be careful on are numbers are 0s and 1s, but not always. It just depends on the situation. Okay? Any guess as to what the student might have done to get to this point? Like, what if this question instead said, how would you respond to the student? That's one of their favorite questions in this book.
They probably just reduced the 5s.
Yeah, they probably did. They probably looked at this and did something like this. And maybe you've even done something like that at some point on accident or whatever. Why doesn't that work? I mean, we know it doesn't because we gave an example. What's wrong?
You have addition on the top, it's not multiplication.
Yeah. There's actually a couple things because it's addition that make this not work. Number one, when you cancel things with addition, they usually become the number 0. Like we add 1, subtract 1, they become the number 0. The other reason that this being addition comes into problem is that when we reduce denominators and numerators, we have to reduce the entire numerator, not just part of it. So for instance, if this had said 5n, and we could have canceled 3 5s, that would be fine. But it didn't say 5n, right? You have to reduce it from all of the pieces. So it doesn't ask about those pieces of information, but it's good to think about them because sometimes those are the kinds of questions that your book will ask about a problem. All right, another kind of pattern that we're going to look at is, this is going to actually be shapes. So these are called figurate numbers. These are based on geometric patterns. They provide examples of sequences that are neither arithmetic nor geometric. Okay, so these are not going to be like the sequences we had before, but they can be represented by a shape of dots. So we're going to start with triangular numbers. And so if you're a visual person, you might really like this particular idea. Triangular numbers, so here's the number 1, and then the number 3 is 3 dots in the shape of a triangle. So that's the number 3. And then the number 5 is 5 dots in the shape of a triangle. I said 5 and I meant 6. My apologies. Oops. And then when I do 10, what do you think is going to happen? I mean, sort of my triangle is sort of growing each time. Yeah, we're sort of going to add a row on the bottom, and the row on the bottom is going to be adding the number 4 to it, right? I'm going to have 4 dots on the bottom. And then I'm basically going to have the same shape I had before. 3 dots above that, 2 dots above that, and 1 at the top. And then the 15 would come from doing what? Yeah, adding 5 dots at the bottom. So these are called figurate numbers. And we can represent them either in sort of the visual imagery you see here, and they correspond to the numerical sequence of the numbers of 1, 3, 6, 10, 15. Just for fun, what would the next couple of them be? What would come after 15? 21, and then 28. And if you weren't sure without sort of thinking about the rows, you could also look at this in terms of the sequence of numbers and what you're adding. So this is plus 2, and then it's
Plus 3, plus 4, plus 1, plus 6, plus 7.
perfect. And just to show you again another sort of instance of this happening, what would happen if we looked at the sequence 2, 3, 4, 5, 6, 7? Yeah, if we go sort of one deeper, we actually end up with something that is in fact arithmetic. Okay, so that's called second differences. Again, we talked about that last time, but we do have that pattern represented there. All right, let's try another one over here. We're going to do square numbers. So the first number is the number 1, just like last time, and then there's the number 4. There's the number 9. My pictures are not perfect. And here's the number 16. Whoops. Pretend they look better than they do. It doesn't look very square. It almost looks like a rectangle now. Sorry about that. It should look square. What would the next one be?
25,
And the next one?
36.
Now, those of you who are responding this quickly have recognized that there's sort of an equation going on here, right? What's the equation that's going on here?
1 squared.
Yeah, we're squaring things, right? Sort of, it's like an x squared, so it's like 1 squared, 2 squared, 3 squared, 4 squared, and so forth. I just want to show you one more time that we can do the same addition thing here, which is kind of cool. So let's actually take a moment to look at that. This is plus 3, right? And then what?
Plus 5,
Uh-huh.
plus 7,
And if we go one deeper, what do we have?
plus 10.
Adding 2's every time. Now, sometimes you have to go more than one deeper. Sometimes you have to go 2 or 3 deeper to find a pattern depending on the sequence you're working with. But power of 2, x squared, we went twice through and it works. All right, this is one of my favorite examples because it really happened in real life, which is kind of funny. All right, so in the fall of 2011, the newly formed Hurley College of Science and Math, that's a part of the college that I'm a part of at OBU, was formed, and we had a meeting. On the board, the value 3.1415 was placed, and we were asked to find the next terms in the sequence of numbers. So without asking or looking around at anybody, I want you to write down what you think the next 2 numbers are in this sequence of numbers. Okay? Now, let us realize that what you're doing when you're writing down those next 2 numbers is you're doing a form of either induction or deduction. Do you remember which one it was? Let me go back to that slide where it says them on there so you can look at it again. Yes, induction. You're making a generalization, what you think is going to happen next, based on observed patterns. And you're trying to decide something based on what you're seeing already in a specific example, right? So induction doesn't always work perfectly. So I want someone to give me an example that you found. What did you write down as your next two numbers? 1, 6. Okay, who wrote down 1, 6? Show of hands. Okay. Did anybody write down anything different? You wrote down 6, 1.
I wrote 1, 4.
Andrew, what did you write?
1, 4.
Why?
I'm just trying to remember the next two digits were in 5.
Okay. So you were doing the other thing is that people do usually. What was that?
The next one, 9.
It's 9, 2. Yeah. So this is sort of looking at the numbers as independent sequence of numbers, right? One number after another. And so you're seeing 1, 4, 1, 5, 1, 6, something like that. Or you might, something of that nature, which is a reasonable assumption, right? I will guarantee you everyone in the room that day did the second one because we're math and science people. And we saw 3.1415 and we said, well, it's pi. What are you talking about? Because that's what our minds went to when we saw those first 4 digits. It wasn't the fact that 1, 4, 1, 5 would become 1, 6, right? So we made sort of one difference that you didn't make, but neither one's right or wrong. I mean, we were both using induction, right? Which doesn't always lead to the same conclusion. So I point that out because I want you to recognize that very fact that sometimes your answers could be different when you're using induction. Now, the ones you're going to work with, by and large, you're not going to have that sort of thing happen. But just recognize that there was one example on a sequence like this, I should have written it down when it happened, where the numbers were small enough and had few enough of them that it could have taken a turn in either direction. Maybe it's one of the ones in your book, as to which you thought it was happening next, kind of like this. So those things do sometimes happen. All right, here's your practice, your homework and your group work. And we will get started.